Yeah, everyone, in this video, we're going to start with the revision of functions. So here we'll have types of graphs, linear, quadratic, polynomial, exponential, log. Then we're going to talk about this transformation, rational functions, asymptotes, and then cubic sum and product. And then we are going to cover this remainder and factor theorem, which will be the last topic, and that's going to be based on AHL. So before that, we should already know what are functions. So I'll just give you a quick intro about it. So functions is basically y is equal to f of x, where y is in terms of x. Now here, when I say y is equal to f of x, so it could be y is equal to x square, y is equal to tan x, y is equal to sin x, whatever. So first we'll start with the basic graph. So the first one is your linear graph. Now what exactly is this linear graph? So you already know it's basically a straight line. So that is nothing but y is equal to mx plus c, which we write it, but I am going to write it as ax plus b, where a and b are nothing but constants. Okay. Now after this, simultaneously I'm going to cover domain and range of each functions, which you already have an idea about it. So domain means what? Whatever the input values we can take, and range means whatever the output values we can get. You can find domain and range with respect to the graph or algebraically. So for example, even if you take an example of y is equal to 2x plus 3, I can put any value of x, so the domain is all real numbers. At the same time, I can get any real number, so that's going to be the range, which is minus infinity to plus infinity. So domain and range here is all real numbers. Now graphically what will happen? So this is nothing but a linear graph, so it will look somewhat like this. So as you can see, whatever the input values are, this is nothing but your x input values, so that is nothing but your x-axis values. So you can see all real numbers. At the same time, if I talk about all output values, that's going to be the range of this function. After that, we have quadratic function, which I can write this thing as y is equal to ax square plus bx plus c. After that, we have ax cube, so these are nothing but your polynomial functions, bx square plus cx plus d. Then we have ax to the power of 4 plus bx cube, and so on till whatever, till e or whatever. Okay, so this can go on x to the power of 4, 5, 6, 7, 8, 9, whatever. Now the thing is, if I talk about y is equal to ax square plus bx plus c, you can even understand through the roots. Roots means what? Basically where the output is 0. In this case, when I talk about y is equal to ax plus b, so here whatever this x-intercept value is going to be, or where the y will become 0, so that is nothing but a root. Like for example, if it is 2x plus 3 is nothing but y, so if I put y is equal to 0, I'll get 2x plus 3 is equal to 0, which gives me x is equal to minus 3 by 2. So this is nothing but your x-intercept, or one of the roots which we get it. Now when I talk about ax square plus bx plus c, if we factorize it, which I am understanding that you already know, so it's going to be x minus 3 x plus 3. I'm just taking an example out of it, x plus 4, let's say. So here I can see that if I equate y is equal to 0, I'll get two roots, which are 3 and minus 4, right? So as you can see, if I get 3 and minus 4 as two roots for this particular case, so here this 3 would be somewhere here and minus 4 would be somewhere here. And obviously if I want to graph if I want to just graph this function, so it should be something which should intersect from these 2 points. So it's going to be like this. So that is nothing but your quadratic graphs. Okay, then it comes to ax cube plus bx square plus cx plus d. I can see that there could be 3 roots. See, there are maximum 3 roots. Okay, there is a possibility of no roots as well, that we can see later. But here if I have 3 roots, 1, 2 and 3, so you see that's going to be this way. If I talk about ax to the power of 4 and something like that, this is what we get. X to the power of 5 and so on, so it's going to be this, this, this and this. And as you can see, 1, 2, 3, 4 and 5 point of intersection you're going to get. That is nothing but your x-intercepts. So maximum 5 roots you're going to get. See, I'm talking about maximum roots. There is a possibility that there could be no roots, there could be 1 root, 2 root, 3 root, all the possibilities are there. Let me give you an example. If I talk about this function ax to the power of 4 plus bx cube and whatever. Now if the graph is like this, so as you can see, it is not intersecting at x-axis. So there is a possibility that it won't even intersect at x-axis. So there won't be any roots. Later you will see that when I talk about the roots, and if the roots are not there, so we can get complex roots, which is the next topic that we will see later. So as of now, you understand the design of these functions, which is linear function, which is just a line, then quadratic, which is just a parabola. This is very important because we are going to use this for the next topic, which is transformations and all of these things. Then ax cube. So as you can see, 3 roots. So one goes up, one goes down like this. It's ax to the power of 4. It goes like this, up and up. To have an idea about how these roots operate, so what we can do, we can simply just put one of the values of x. Generally, when I want to talk about the range and domain for this one, let's say, so what I'll do, I'll just put x is equal to a huge number, maybe 1000, 10,000 or something like that. So as I can see, if it is ax to the power of 4, when I put 1000, 10,000 in this case, so I'll get 1000 to the power of 4. So obviously it's going to be a huge number. So here it will go like this. But where even if I put minus 1000 as x value, and if I put minus 1000 to the power of 4, then also I'll get a positive huge number. So that's why both ways it's going up. Here also both ways it's going up, like this and like this. But if you talk about ax cube function, or in fact for that matter ax plus b function, like where the degree of the polynomial is odd, 1 or 3 or whatever for that matter, so that time if I put x is equal to, in this case let's say, if I put x is equal to 10,000 or something like that, so then you will get positive 1000 cube whatever. But if I put minus 1000 here, so it's going to be minus 1000 to the power of 3, which is going to be negative something. So as you can see, it will be, I mean in this case it will be like this. So one side will go up, one side will go down. So as of now, you should just know how to draw these graphs. So we have covered linear, quadratic, polynomial. Now next part is the other type of graph. So trigonometry, of course we are going to do it later, but there are another set of 2 graphs. One is your, let's say y is equal to, I'll just take an example of 2 to the power of x, which is actually a to the power of x kind of a graph, where a is nothing but a constant, like y is equal to a to the power of x. So I'll take an example of y is equal to 2 to the power of x, and the inverse of this graph, which is I'll make x as the subject. So that is nothing but 2 to the power of x is equal to y. If I want to make x as the subject, so x is going to be what? X is going to be log y to the base 2. So the inverse function is y is equal to log x to the base 2. By the way, this is nothing but your tick mark rule, which is if I have a to the power of b is equal to c, and if I want to convert that into logs, so all I have to do is I'll just have to make b as the subject. So I'll just move this b down, a this side, so I'll get b is equal to log c to the base a. On the other hand, if I have log a to the base b is equal to c, and I want to convert this in terms of exponent form, so again I'll use tick mark rule, so I'll get a is equal to b to the power of c. So these are nothing but the like just a tick mark rule for this logs thing. Now how about these graphs of 2 to the power of x as well as this one, which is log x to the base 2. So see, again here there could be an issue with respect to domain and range. So what could be the thing? So generally if I want to find out domain and range of these kind of functions, so what I do, so I simply put x is equal to a huge number, just like in this case also we have put certain numbers. So here also I'll put a huge number, maybe 1000, 10,000 or something like that. I can see it can go till infinity, but like 2 to the power of 1000, of course it's a huge number, so I can see that it's going to go towards infinity. So I'm going to put 3 values. One is this infinity, the other one I'm going to put it as 0, like the middle value whatever, and then I'm going to put minus infinity. So infinity pe to I'm getting infinity value. At 0 I'm getting 2 to the power of 0, which is, you already know, which is 1. Anything to the power of 0 is 1. So this is what you get. And then if I put minus infinity, so generally people assume that minus infinity, if I put it, it's gonna be like negative infinity all the time. But no, here just take an example. If I put 2 to the power of minus 10, let's say, it's like 1 upon 2 to the power of 10, which is 1 upon 1024. So it's a very small number. So the thing is, when I put minus infinity, like minus 1000, 10,000, so it's going to be 1 upon 2 to the power of 1000, which is still positive, but it is going towards 0. So that is nothing but your, like it will just go towards 0, but it will never be 0 until and unless we get minus infinity as the value. So you see the graph will be somewhat like this. So 2 to the power of x graph, will look somewhat like this. So as you can see, the domain of this function would be all real numbers, because as you can see graphically also you can think about it. At the same time, if I talk about the range, it's gonna be above 0. Now see, you don't have the value of minus infinity, so that's why you cannot get a 0 as the output. So that's why the domain of this thing is all real numbers, but the range would be what? So range would be y is greater than 0. Now if I talk about the inverse of this function, which is log x to the base 2. So let me just write it here. So we are talking about y is equal to log x to the base 2. Remember, this is nothing but the inverse of this function. So there are a couple of things which I'm going to tell you. First is how to draw it. So as you already know how these logs operate, in case if you don't, one second. So like if I have log 4 to the base 2, the base is gonna be same, and then we have log 8 to the base 2, then we have log 16 to the base 2, whatever it is. So what exactly it is? 2 to the power of what will give me 4, so it's gonna be 2. 2 to the power of what will give me 8, it's gonna be 3. 2 to the power of what will give me 16, so it's gonna be 4, and so on. So we are converting these huge numbers to very small numbers, like 8 is transformed into 3, 4 is transformed into 2, and so on. So let's put these values. So if I have put x is equal to 2, so I'm gonna get 1. So let's say 1 is here, so 2 is here. So if I put 2, I'm getting 1. If I put 3, like it's gonna be in decimal. But if I put 4, I'm gonna get 2. So if I put 8 and so on, so it's gonna be somewhere like this. So as you can see, the graph would be somewhat like this till now. But if I put log 1 to the base 2, so that is what? So 2 to the power of what will give me 1? So anything to the power of 0 is 1. So this is what the graph will look like. But now, if I put small values like log of 1 by 2 to the base 2, log of 1 by 4 to the base 2, log of 1 by 8 to the base 2, and so on. So using log properties, what we will get? So 2 to the power of what, 1 by 2 to the power of what will give me, 2 to the power of what will give me 1 by 2, so it's going to be 2 to the power of minus 1, so it's going to be minus 1. This 2 to the power of what will give me 1 by 4, so minus 2, this is minus 3, and so on. So you see, this is what the graphs look like. So this is your log graph. Now as you can see, this graph is nothing but a reflection over y is equal to x. So whenever you want to draw the inverse of the graph, all you have to do is you just have to draw this y is equal to x line, and then you just reflect it over y is equal to x. Whatever the graph you are going to get, that's going to be the inverse of this graph. In fact, even if I have, let's say, this kind of a graph like this, I don't know what kind of a function is this, but if I talk about this graph, then if I want to find the inverse of it, so I'll just reflect it over this. This is what we'll get. So these are your basic graphs, which are linear, quadratic, polynomial, exponential, and log functions. Log, again, we will see that later, but at least you got an idea about the basic kind of functions. Now the next part of this is transformation. So what I would recommend, that always take y is equal to x square as your reference to understand the transformation. So in general, first of all, let me tell you what exactly it is. So the first one is your translation. Transformation is basically like, just changing the graph. So the first of that is basically your translation. In that we have vertical translation as well as horizontal translation. And remember one thing, whenever it stands for vertical, of course, it is with respect to y-axis, so that's why vertical. Horizontal is with respect to x-axis, that's why horizontal. Okay. In general, what we have, so if I have y is equal to f of x, and there is a change in y, so that means what? I'm talking about y minus 2 or y plus 2, something like that, is equal to f of x. So I am transforming this normal function f of x to y minus 2 f of x, and this normal y is equal to f of x to y plus 2 is equal to f of x. Now if you see, so this is not a function, but I'm just giving you as a reference. So let's say this is a function. Okay. In that, if I make it y minus 2 is equal to f of x. Now remember one thing, whenever it is minus 2 or it's a negative, so it will always be opposite, be it for translation, reflection, then dilation, whatever we want to understand. So it is always going to be with respect to opposite thing. Geometrically, it will go 2 steps up but algebraically, as you can see, it is y minus 2. So it is always opposite. Keep that in mind. So maybe if the function is something like this, f of x plus 2. So what we are going to do, we are going to shift this plus 2 to the other side, and we'll understand it's a change in y. Similarly, this function would have been minus 2, f of x minus 2. So it's a change in y. So it was plus 2. Like minus 2, if I shift it to the other side, it's going to be plus 2. So let me just put it like this green part. So as you can see, like when it comes to y minus 2 is equal to f of x, the design remains same. It is just shifted 2 steps up. On the other hand, if I talk about y plus 2, so that means what? It will take 2 steps on the negative side of y axis. So it's going to go 2 steps down. So the design remains same. It will just be shifted. Not here. So like this point will be shifted 1 and 2 steps here. So here it's going to be. So it's always going to be opposite. So this is nothing but your vertical translation. And of course, with respect to horizontal, what will happen? So if I have y is equal to f of x minus 2, and if I have y is equal to f of x, I'll just take plus 3. So what will happen with respect to this situation? So again, same star, I'm going to take it. This time, if it is x minus 2, so it will take 2 steps on the right hand side, on the positive side of x axis. So 1, 2 like this. Design remains same. It will just be shifted. When it comes to x plus 3, so it will take 1, 2 and 3 steps on the negative side of x axis. 1 second, I'll just highlight it with the red. So it will take 3 steps on the negative side, 1, 2 and 3. Design remains same. It will just be shifted. So this is with respect to a random diagram. This is valid for any your trigonometric functions, exponential function, logarithmic function, whichever function you say. If I change this x to x minus 2, horizontally it will be shifted. If I change y to y plus 2, vertically it will be shifted. Up, down, left hand side, right hand side, depends. And it is always going to be opposite. So let me take an example of a quadratic function. So if I have, let's say, y is equal to x minus 3 whole square minus 5. So here what will happen? So first I'll shift minus 5 to the other side. I'll get y plus 5 is equal to x minus 3 whole square. Now see, this is with reference to the graph which is y is equal to x square. Like this. So this is your y is equal to x square graph where the vertex is 0, 0. I assume that you already know all the parabola terms, vertex and x-intercept, y-intercept, whatever is needed. So here if I say y plus 5, you can go in any direction. You can do horizontally first and then vertically, up to you. So now when it comes to plus 5, so it will take 5 steps on the negative side, opposite. So that's why 1, 2, 3, 4 and 5. And then x minus 3, horizontally it will shift 3 steps on the right, 1, 2 and 3. The design remains same. It will just be shifted. So this is what the parabola looks like. And as you can see, the vertex would be what is going to be 3 right, so 3 and 5 down, so minus 5. That's going to be the case. If you want to understand this graphically, so I have just plot this thing on graph. y1 is equal to x square and y2 is equal to x minus 3 whole square minus 5 on GDC. So if I just draw it, this is what we get. So as you can see, for the blue part, it's going to be this, and for the red part, it's going to be this. By chance, if you want to know the vertex, so what we will do, we'll just G-solve it and we'll find this is nothing but a minimum point. So it's going to be minima. For this would be how much? So 0, 0. And G-solve minima for this other graph. So I'll just go on the right hand side, or 1 second. Yeah, down, execute. 3 and minus 5 is nothing but your vertex, as you can see. By the way, again, coming back to something called domain and range. So here in this case, obviously, if I talk about this blue graph, so here what will happen? I can see that parabola will go this side as well as this side. So if I talk about the range, domain of this graph, so it's going to be all real numbers. Same goes with this one, all real numbers. But if I talk about range of blue graph, I'm talking about. So if I talk about the range of this blue graph, I can see it is only this much. So it's only the positive side of y-axis. So the range would be what? So the range would be, for the blue one, y is greater than equal to 0, including 0. And same with respect to this green graph, if you see, domain, all real numbers, because I can see it's on the x-axis. As you can see, it will go like this, it will go like this, no problem. But if I talk about the range, so the range this time would be what? It will start from here. So this to this. So as you can see on the y-axis, it will start from here. So it will be with respect to this minus 5. So here the range would be what? Y is greater than equal to minus 5. So this is the first one, which is your translation. Now let's move on to the second one. Now the second one is your reflection. As you can see, this is actually horizontal and vertical are two transformations, but we have just combined it. The next word is reflection. Again, as I told you that we will always take y is equal to x square as our reference graph. So what will happen first? So first, if the graph y is equal to f of x, of course, in general y is equal to f of x has been transformed to, one is y is equal to minus f of x and the other one is y is equal to f of minus x. So here what will happen? Now as you can see, if it is y is equal to minus f of x, it's not a change in x, it's a change in y. So actually I can write this thing as minus y is equal to f of x. Right, this though as it is, like I have just transformed f of x to f of minus x. Now what will happen? By chance, if you ever get confused, even I use the same thing. So I'll just keep this y is equal to x square as a reference graph. Now the thing is, if I change y is equal to x square, like maybe I can just put it like this. So y is equal to x square has been modified to minus y is equal to x square, which is actually y is equal to minus x square. So what will happen? So this graph, you know quadratics, how it works. So when it comes to minus x square, when the coefficient of x square is negative, it will always be downward facing. So here, this was the original graph, but this time the graph would be what? The graph would be downward facing. So as you can see, when it comes to something like this, the y is getting changed to negative. It's a reflection over x-axis when y is getting transformed. Again, opposite. See, it also works here. On the other hand, if I talk about this graph, when it comes to somewhat like this, y is equal to f of minus x. So here what will happen when I transform y is equal to x square to y is equal to minus x? So see, we are replacing x with minus x. So it's going to be minus x whole square. So which will remain as it is, y is equal to x square. So the graph which was supposed to be like this previously is same as it is even after transforming it to x to minus x. Why? Because this one is a reflection over y-axis. So here when x is getting changed to minus x, it's a reflection over y-axis. That's it. Yeah, so as you can see, when it comes to minus y is equal to f of x, something like that, it's a reflection over x-axis, and when y is equal to minus, like f of minus x, so it's a reflection over y-axis. Okay. Anyways, then we have the last transformation, which is with respect to dilation. So what exactly is with respect to dilation? So again, we have two dilation, which is vertical as well as horizontal dilation. Again, we are going to take y is equal to x square. See, remember, if you ever get confused with what kind of a dilation it is, or vertical, horizontal, in fact for that matter reflection or something like that, remember, just take y is equal to x square as a reference graph and we will see it. So if I have y is equal to x square and we transform it to y is equal to 4x square, the thing is, what we can do, we can either make it like this, that it is y by 4 is equal to x square, or we can write this thing as y is equal to 2x whole square. So in this case, when it is y by 4, it's a vertical dilation for sure. When it is with respect to this 2x, it's a horizontal dilation for sure. The next part is, what about scale factor? So scale factor, whatever scale factor, and as I said earlier, that it is always going to be opposite. So when it is y by 4, it's a scale factor 4, like 1 by 4 it is, so it's going to be 1 by 4, which is going to be 4. And here when it is a scale when it is 2x, so it's a horizontal dilation of scale factor 1 by 2, opposite always. Now let's understand what exactly it means. So see, we know the graph of y is equal to x square, which is going to be somewhat like this. Whatever. And then the transformed graph, which is y is equal to 4x square, I'll draw it like this. This is how it looks like. Vertex remains same for both the cases, 0, 0, whatever the case. Now, what exactly is happening vertically and what exactly is happening horizontally? Both the graph is same, but let's understand with respect to the values. So let me just create one table to have an understanding. So these are your x values, this is your f of x values, and this is your transformed f of x values. Let me just write this thing as g of x. So this is your g of x, meaning this is your x square and this is your 4x square. So obviously 0, 0, 0 to will remain same. But if I talk about 1, I'll get 1 here, I'll get 4 here. If I put 2, I'll get 4 here. 4 times 4, it's going to be 16 here. If I put 3, it's going to be 9 and it's going to be 36. Then if I put 4, I'll get 16 and 64. I think this much is enough. But take it, 5, 25 and 100. And here 6, 36 and 144. So these are the 4x square values and x square values. Now what exactly happened? So see, vertical dilation is quite simple. Vertical dilation of scale factor 4. That means what? As you can see, I'll just highlight vertical dilation with the green values. So as you can see, what exactly is happening? Vertical dilation of scale factor 4, meaning the output values or the y values are becoming 4 times of the original function values. So that means what? When it was 1, now this is 4 times of 1. When it is 4, it is 4 times of 4. When it is 9, it is 4 times of it. So you see, it's just all multiple of 4. If you talk about with respect to graph, what happened? Previously, I used to get at 1, I used to get 1 as 1 in the previous graph output. But here I'm getting 1, 2, 3 and 4 times of that, which is going to be 1, 4. Right? Now, horizontal dilation would be what? So I'll just represent that with respect to the red part. So horizontal dilation of scale factor half. Okay? Horizontal dilation of scale factor half, not 4 or something like that. It's a horizontal dilation of scale factor half. So what will happen? So see, look at this. So previously I used to get 4 as the output at 2. Now I'm getting that same 4 output at half of the value which is at this x. Previously I used to get 16 as the output at 4. Now I'm getting that same 16 output at half of the value, which is 2. Previously I used to get 36 as the output at 6. Now I'm getting that same 36 output at half of the value, 3. So if you see, in both the cases, like obviously it's the same graph, the output graph is increasing, like it is giving me the increased value. So when it's a vertical dilation of scale factor 4, that means what? This is understood that it's 4 times the original value. But when it is horizontal dilation of scale factor half, so that means what? That same output which I used to get at 5, at 10 or 20 or something, now I'm getting that same output in half of the value, which is 5 or 10 respectively. So here, like what will happen? So see, I used to get this output, let's say at 2 I was getting 4. At 1 second, I'll just change the color. So yeah, at 2 I used to get 4 as the output. Now, so at 2 matlab like this here. Now same 4 output I'm getting at half of the value, which is at 1. So now that same 4 output I'm getting at half of the value. Okay. So in general, if I have, let's say, y is equal to 3 f of x by 5. So what we'll do, first I'll shift this 3 to the other side. I'll get y by 3 is equal to f of x by 5. So here y by 3 means what? It's a vertical dilation of scale factor 3 opposite, and here it's a horizontal dilation of scale factor 5 again opposite. So now we're going to start with this thing, which is rational function. See, in the previously we have covered all these type of functions, which is linear functions, quadratic, polynomial, exponential, log, whichever are there. Then we have set of rational functions. So what exactly it means? Whatever these cubic linear functions are there, they are in terms of like this, like something upon something, numerator upon denominator. So maybe something like this, 1 by x, 1 by x plus 5, then 1 by x square plus 2x plus 5, and in fact for that matter x plus 5 upon x cube plus 7x square plus 8x. All of these are nothing but your numerator and denominator. Wherever you see in terms of polynomial, that is nothing but your rational functions. So first let's start with the basic one, which is 1 by x. So how the graph will look like for this 1 by x function. So as you can see, and see, all the rules will be applicable for other rational functions as well, like basically all those transformations. So if I talk about this 1 by x function, so remember, in fact, even when I talked about the domain and range of these functions, so what I said that consider three values. One is minus infinity, the other one 0, and then infinity. You will get an idea about the range for that. In 1 by x, you can put all the values of x except for 0, because we cannot have 0 in the denominator. But even if you put it, you can see that it will go towards infinity. Positive or negative, that depends. So this, wherever the denominator is 0, that is nothing but your vertical asymptote. So it will remain same throughout all the rational functions, that whenever the denominator of the function is becoming 0, so that will be your vertical asymptote. So in this case, x is equal to 0 will be your vertical asymptote. In this case, x is equal to minus 5 will be your vertical asymptote. Now let me talk about this 1 by x first. So if I talk about this 1 by x graph, at 0 to we are getting asymptote. So that means what? It's going to be just infinity. So this is what the asymptote will look like. And then if I put certain values, let me put x is equal to 1, so I get 1. If I put x is equal to 2, I'm going to get 1 by 2. 3, 1 by 3. 4, 1 by 4, and so on. At the same time, if I put x is equal to, for this one, let's forget this. So if I put x is equal to 0.1, I'll get y is equal to what? 10. If I put 0.01, I'll get y is equal to 1 by 0.01, which is 100. So as you can see, when it is closer to 0, that time the output of 1 by x would be huge. So as you can see, it's going to be this way. So you see, this is going to be the graph of 1 by x. But on the negative side, what will happen? So again, I'll start with minus 1. So if I put minus 1, I'll get minus 1 as the output. If I put minus 2, minus 1 by 2, minus 3, minus 1 by 3, and so on. Then if I put minus 0.5, so it's going to be minus 2, minus 0.1, so minus 10. So in fact, I replace this minus, I replace the 0.1 with minus 0.1, I get minus 10, this, and so on. So you see, this is what the kind of graph you're going to get. So this is your rational function ka basic graph. Now if I just make it 1 upon x plus 5, like y is equal to 1 by x plus 5. So here what will happen? So you can do it in two ways. The first one, with respect to transformation, it will be very simple. So this would be a reference graph 1 by x. Now I'm just making this x as x plus 5. So it will take 5 steps on the negative side, 1, 2, 3, 4, and 5. And the design will remain same, it will just be shifted. This is what the 1 upon x plus 5 will look like. Okay. But what I prefer, you just use little bit of logic, that when it is 1 upon x plus 5, so you just look for vertical asymptote as well as horizontal asymptote. Horizontal asymptote we'll understand later. But right now, if I talk about just vertical asymptote, so wherever the denominator is 0, that means what? If I put x is equal to minus 5, so I'll get this as vertical asymptote, which will be somewhere here. So this is your asymptote, x is equal to minus 5. So x is equal to minus 5 is your vertical asymptote. Okay. Now let's talk about horizontal asymptote. So let me take a different example altogether. We'll just continue this later after this horizontal asymptote thing. So if I have y is equal to 1 upon, I'll just modify a little bit, x plus 5, same, minus 3. So here you can either shift minus 3 to the other side, and then you can apply transformation, like it's y plus 3, so it will take 3 steps down, and x plus 5, so 5 steps on the negative side. That way also you can do it. Otherwise, go for horizontal and vertical asymptote. Vertical asymptote, same, it's going to be x is equal to minus 5. But if I go for horizontal asymptote, so see, when the output is infinity at a certain value, that is your vertical asymptote. Like as you can see, the output is going towards infinity here. But if I put input value as infinity, like x is equal to infinity, like a huge number, whatever, negative infinity, positive infinity, does not matter. So if I put that value, and if the output is going towards a constant, that is nothing but your horizontal asymptote. Meaning, if I put x is equal to, let's say, 5, so here y would be what? Y would be 1 by 10 minus 3. Still, you know, there is certain value for it. But if I put x is equal to 5000, then y would be what? Y would be 1 upon x plus 5. So 5000 plus 5. So 5005 minus 3. Now this is like a very small number, like almost 0, I can say. In fact, if I put x is equal to, now think about it, an infinite value I put it, like, you know, like 5 trillion, billion, whatever value you want to consider, like this. So this value, if I take it, so it's going to be 1 upon 5, this many zeros, minus 3. Now this thing is 0, like literally 0. If I put infinity, then to definitely it's going to be 0. Infinity we don't know, infinite value we don't know. So as you can see, the output is going towards infinite value, which is when the input is going towards infinite value, the output is going towards this minus 3 output, like minus 3. So that's why here for this graph, what I'm going to do, I'm going to first draw the vertical asymptote, which was at minus 5. So it is somewhere here. And then I'm going to go for, once again, I'll just make this with red. Okay, where the output is infinity. And if I go for horizontal asymptote, which is going to be minus 3. So it will be somewhere here. Okay. Now all you have to do is you just have to draw the graph which satisfy this condition. So there could be two cases. Either the graph would be this way, like this, or it could be this way. If you want to verify how the graph would be, like this one or that one, you can go for y-intercept. Put x is equal to 0. I'll get 1 by 5 minus 3. So 1 by 5 minus 3 is above minus 3. Like, one second, I'll just write it down here. So if I go for y-intercept, so I'll put x is equal to 3. So y is equal to 1 by 5 minus 3. And logically, think about it. It's like minus 3 and little bit above minus 3. So it's going to be this 3. This is any which way is x is equal to minus 3. Y is equal to minus 3. And this is x is equal to minus 5. So you see, this point is slightly above it. So that's why this is what the graph will look like. Whatever, the y-intercept is what. So if I put x is equal to 0, it's like minus 14 by 5 after solving. Like lesser than minus 3 for sure. So the modulus value. So this is nothing but your minus 14 by 5. That is nothing but your, like this is how the graph will look like. Now let's understand this horizontal asymptote, vertical asymptote with other rational functions. So see, we have 4 cases for these type of rational functions. So the first one is when it comes to something like this, which is like x cube plus 7x square plus 8x plus 5 upon x plus 5. See, at the end of the day, if I know vertical and horizontal asymptote and one y-intercept, I'll be able to draw the graph for sure. The other one I'll consider as x plus 5 upon x cube plus 7x square plus 8x plus 5. Then I'm going to consider x to the power of 4 plus 7x cube plus 8x square plus 9x plus 5 upon 5x to the power of 4 plus 7x cube plus 8x square plus 9x plus 50. Whatever, doesn't matter. So first 3 cases we will understand, then we are going to talk about this 4th case. Now see, here as you can see, the degree of numerator is greater than the degree of denominator. Like the degree, the polynomial degree I'm talking about. Here the degree of numerator is lesser than the degree of denominator. And here the degree of numerator and denominator are same. Okay. So these are your 3 cases which we are going to get. Now, obviously for vertical asymptote, there is for all of these things. In fact, even if I talk about that 4th case, it's going to be the same thing. So for vertical asymptote, wherever the denominator is 0, that time we will get the vertical asymptote. Okay, like for example here x is equal to minus 5 is your vertical asymptote. Here you can factorize it. Maybe you will get x minus 3, x plus 5, x plus 3 or something like that. So here the vertical asymptote would be at x is equal to 3, at x is equal to minus 5, and at x is equal to minus 3. 3 vertical asymptote we are going to get. Here maybe there is a possibility of 4 vertical asymptote, and there could be a possibility that there won't be any vertical asymptote if we are not able to factorize this one. So then obviously there is a possibility that there are no vertical asymptote in this case. So wherever denominator is 0, that time we will get vertical asymptote. Now we'll talk about the horizontal asymptote. So now see, logically think about it. As I told you, horizontal asymptote we will only get when I put x is equal to a huge number, infinite value. So in this case, if I put x is equal to infinity, so what will happen is going to be infinity cube plus 7 times infinity square plus 8 times infinity plus 5. compared to that, like numerator may we have infinity cube, denominator may we have small infinity thing. So of course the numerator value would be huge, like really huge as compared to the denominator value. So that's why here we won't have any vertical asymptote, because the value is not going towards constant. On the other hand, if I talk about the second case, so here the denominator's degree is huge. Like if I put infinity, like billion, trillion, something value. So numerator mein there is just billion plus 5. In denominator it's billion cube, which is comparatively quite huge as compared to the numerator. So that's why in this case, the horizontal asymptote would be what? It's gonna be 0. Simply 0. Because as the value is going towards infinity, this value maybe would be around 1000 or something like that. But the denominator value at the same time would be in billion, trillion, something. So that's why overall the value will go towards 0. So that's why horizontal asymptote would be 0, fixed. But when it comes to something like this, where the degree of numerator and denominator is same, so that time what will happen? So here, like just consider infinity as a constant. Like infinite is a number which is like in trillion, something like that, 10 to the power of, I don't know, some thousands of value. So but at the end of the day, let's consider that as a constant. So what I'll do, I'll just take out this x to the power of 4 constant outside from the numerator, and at the same time I'll take out x to the power of 4 constant from the denominator. Here what I'm gonna get, I'll get 1 plus 7 by x plus 8 by x square plus 9 by x cube and plus 5 by x to the power of 4. On the other hand, if I take out x to the power of 4 here common, it's going to be 5 plus 7 by x plus 8 by x square plus 9 by x cube and plus 50 by x to the power of 4. Now, if I consider this infinite as a constant, so it's infinite to the power of 4, which I can cancel from here and here. So what am I going to get? And these values will be 0, because something by infinity is always 0. So this 0, this 0, this 0, this 0. So what I am left with, it's just 1 by 5. So here the asymptote would be, horizontal asymptote would be 1 by 5. So in this case, when the degree of numerator and denominator is same, is just coefficient of the highest degree of numerator upon coefficient of highest degree of denominator. That's gonna be your horizontal asymptote. And then there is just one special case of this first condition when it comes to something like this, x cube, we'll take x square plus 7x plus 8 upon x plus 5. When the degree of, you will say that there is no vertical asymptote, which is correct for this part, but there is another asymptote which can be there, which is nothing but your oblique asymptote. Like the name suggests, it is going to be like oblique. So what exactly it means? So when it comes to something like this, x square plus 7x plus 8 upon x plus 5, or the degree of numerator is just 1 above the denominator. Even for that matter, if I have x to the power of 40 plus 7x to the power of 8 plus and so on, upon 5x to the power of 39 plus 8x to the power of 3 and so on. So here there is a possibility of oblique asymptote, just 1 degree above the denominator. So that time what will happen? So like say in like when you were in grade 9, 10th, whatever, so that time when we had 7 by 3, we used to write this thing as, it's an improper fraction, then we convert it into mixed fraction, it's going to be 2 1 by 3. So that time we used to use this long division thing, 3 7. So 3 times 2 is nothing but 6, you subtract, you get 1. So we get 2 1 by 3, like quotient plus remainder upon divisor. So same thing we will apply here. So when it comes to x square plus 7x plus 8 upon x plus 5, so here we will just use little bit of long division. So it's going to be what? I'll multiply by x to get x square plus 5x. Then I'll subtract. This will be minus, this will be minus. I'll just cut this thing. It's going to be 2x plus 8. Then x plus 2. Then it's going to be 2x plus 10, which is, we'll subtract, and then this is what we get, which is going to be minus 2. So overall this function can be written as quotient, which is x plus 2 plus minus 2 by x plus 5. Now in case if you want to understand this remainder and factor theorem, you want to understand this long division in detail, make sure to comment so that I can upload the video for this as well. So here I'll get x plus 2 minus 2 upon x minus 2 upon x plus 5. Now here, in this case, what will happen? So this is your normal function, whatever, it's a same value function. So here, again, vertical asymptote to simple hai, wherever the denominator is 0. That means what? When I put x is equal to minus 5, we will get the vertical asymptote. But if I talk about horizontal asymptote, we are going to put infinite as the value. Now the moment I put infinite as the value, so let me just write it, x plus 2 minus 2 upon x plus 5. So you see, when I put a huge number here, this denominator will be a huge number. Overall, this term will be 0. But as you can see, if I put huge number like 100, 1000, 10,000, so this function y will go towards x plus 2, which is nothing but a line. This line is nothing but y is equal to x plus 2, which is your oblique asymptote. Let me just help you with the calculator to understand this in depth. So see, let me just draw this function. Now see, I have drawn these two graphs. I've just typed this x square plus 7x plus 8 upon x plus 5, the same one, and this x plus 2, which is this line. So as you can see, if I draw this graph, so this red line is your x plus 2 graph. Like maybe I can just put it like this, x plus 2, so it would be somewhere here. And vertical asymptote was x plus 5, which is minus 5. So minus 5 will be somewhere here. So this is your vertical asymptote, this is your like oblique asymptote, or this line. So as you can see, the graph becomes vertical asymptote at x is equal to 5. Like at minus 5 it will go towards infinity, no problem. But as the graph goes towards, the value of x goes towards infinity, so that time it will just be this line x plus 2. So it will meet somewhere. Here also, this will be minus infinity, like it will be a vertical asymptote here. But then when I put x is equal to infinite value or something like that, so that time it will just be a line. So it will match somewhere here. So as you can see here also. So this graph, this red line will go, like when the input value is going towards infinity, so this red, it will just match the red line properly. And vertical asymptote will remain same. So overall, what I wanted to say, that if I put x is equal to infinity or a huge value here, this term will be 0. Like this term will be 0. But then y will follow x plus 2. Just like in this case, when I was talking about a horizontal asymptote. So here, when I put x is equal to infinity, that horizontal asymptote is going towards 0. Like it will touch 0. It will be almost 0 when I put a huge number value. In this case also, when I talk about x cube plus 7x square plus 8x plus 5. So here too, when I put x is equal to infinity, so that time the output is also going towards infinity. It was not going towards the constant. So that's why here I have written vertical asymptote, but it was, horizontal asymptote. So there are no horizontal asymptote at all. So this is what the concept of horizontal, vertical and oblique asymptote looks like. Remember just one thing, that again in oblique asymptote there is no horizontal asymptote, but there is an oblique asymptote as well as vertical asymptote. And of course, if you want to draw it this in paper 1 or something like that, again go for y-intercept. Once you get a y-intercept, either it will be below or it will be above. If it is above, then it's going to be this way. If it is below, then it's going to be the other way around. That's it. So guys, if you have come this far, so we have covered like types of graphs, then your quadratic, then all types of transformations, then rational functions, all of these things we have covered, including oblique asymptote and all. So if you like this video, please make sure to follow, subscribe, and of course share it with your friends. Thank you.